Hello everyone, I hope you all are doing good and welcome back to another video for modern physics that is focusing on atomic structure. So it's going to be a really helpful video if you're studying from Arthur Beiser, since this topic is actually being discussed from Arthur Beiser, which is a great video if you're taking university level modern physics course in your freshman year or sophomore year. So let's begin. Now, for a long time, for centuries, scientists knew that matter has a definite structure at the microscopic level despite appearing continuous. For example, if I see this table, it's a solid matter, right? And although this structure it appears continuous, there is something going at the microscopic level, and that is definite. Now, we do have this definite structure in the form of the modern day atomic structure that we see, right? And not only do we know about atoms, but we also know about the subatomic particles. So we know that every atom consists of protons, right? And neutrons, which together make up the nucleus of your atom. And then there are tiny electrons, which are orbiting your nucleus. So this is a very rough structure. It's not accurate. I know the number of protons to electron ratio doesn't make sense here, but let's just suppose we're talking about a modern day atom. So this is the structure that we have. But earlier on, this was not the case, and there were a lot of postulates being made. To Before we move further, you should know this one thing, that it's a very interesting concept that we have today of how electrons they orbit the nucleus like planets. They orbit the sun. I'm sorry, I'm making a green sun, but like let's suppose this is the sun, and all the planets there are at definite distances from the sun. So this was a very interesting concept, but classical electromagnetic theory denied the possibility of stable electronic structures. And to resolve this, in 1913, Bohr applied the quantum ideas to atomic structure. And it still remains a very convenient way to picture the modern day atoms. Now, before we begin, let's just go over a few ideas on the structure of atom that we have had over the centuries. Before, obviously we know the modern day structure. So during the late 19th century, we knew that chemical elements consist of atoms with electrons. Now, atoms had an overall neutral charge, whereas electrons had a negative charge. So scientists did know that there must be some sort of positive charge in the nucleus that is going to balance out all this negative charge, which helps to get that overall neutral charge for your atom. But they were not sure how. And to resolve this, J.J. Thomson gave the idea of an atom having the appearance of a fruit cake, in which he basically suggested that electrons were embedded in a positively charged mass. So let me show you how this looks. So let's suppose this is a positively charged mass, and you have your electrons of, let's say, this color, and your electrons are evenly spread out throughout this positively charged mass. This is a positively charged mass, and electrons are evenly spread out throughout the volume. But later on, to confirm this concept, there was another experiment that occurred, and that was done by Hans Geiger and Ernest Marston. And this experiment is called as the alpha particle scattering experiment. Now, in this experiment, alpha particles were used like probes to strike at a gold foil. And before we move forward, let me tell you what an alpha particle is. So alpha particles are basically helium atoms which have lost their electrons, and therefore this helium atom, it has a plus 2e charge, right? So they're helium atoms which have lost 2 electrons. And now let me show you how their experimental structure looked like. So you can observe you can observe this image. So basically, they took a radioactive substance which was releasing alpha particles, and then they took a lead screen with a small hole in it, so that alpha particles could move through this very small hole and direct towards the thin metallic foil, which in this case was made up of gold. And then after that, there was like this zinc sulfide screen which was placed at one end with a traveling microscope to observe the pattern of alpha particles. Now thin metallic foil could have been of any other element as well, but gold was specifically chosen because it was a heavy element and it was supposed to give the results that they were desiring. So what they were basically expecting was that all the atoms will pass all the alpha particles will pass straight through the foil with very little deflection. However, this was not the case, and the actual results that came about were shocking, and you can observe them right here in this diagram as well. So as you can see, most of the alpha particles are indeed traveling straight like this, but some of them are being deflected at very large angles. And then there is another class of the alpha particles which are even being reflected backwards, or they're being deflected backwards. So why was this? Now, Giger and Marston made some conclusions. And they made it on the basis of the fact that the alpha particles that they are using are relatively heavy, which is around like 8,000 electron masses, okay? And not only are they heavy, but they were being accelerated to very large speeds, almost 2 into 10 raised to power 7 meters per second. So only powerful forces could have caused such marked deflections. Now they made certain conclusions based on the results that they saw. And let's write the conclusions here. So the first conclusion that they made was that there was a tiny nucleus with positive charge in an atom. So there is a tiny nucleus with positive charge in an atom. The second conclusion that they made was that all mass is concentrated in the nucleus and electrons are some distance away. So all mass is concentrated in the nucleus and electrons are some distance away. We can say that the nucleus is very dense. The third was that most of the atom is an empty space. Now these conclusions supported the fact that most of the alpha particles simply pass through because most of the atom in itself is empty. And it also answers why alpha particles, some of the alpha particles deflected at large angles as well. So you can give it a guess. Why was it so? Just pause the video and think of why some of the alpha particles deflected backwards. So they were able to deflect backwards when the alpha particles, they fell on the regions where the dense nucleus with positive charges was located. And then also the atomic electrons, because they were being so light, the electrons, according to this model, they were so light, they could not cause a lot of deflection, and which is why most of the elements, most of the alpha particles were able to pass straight through. So I'll draw the structure of atom as provided by Rutherford in conclusion to the Giger-Marston experiment. So this is how this looked like. You have your positive structure, right? Let's erase this bit and let's take another color for electrons. And then your electrons were sort of like surrounding this positive charge. Not exactly quantized, but like still somewhat similar to the planetary model of atom that we have today. So this is the kind of structure that we got as a result of the Giger and Marston experiment. Now later on, these experiments were done with different elements, and they determined to they help to determine how alpha particle scattering जो है, it determines the nuclear charge, uh, which is represented by Z as well. So they help to determine the nuclear charge of different elements. Comparison of relative scattering of alpha particles by different foils provided a way to find the nuclear charge of different atoms involved. And also, atoms of any one element have the same nuclear charge. These are the results of the later experiments which were performed with different atoms. Okay, so atoms of any one element have unique nuclear charge secondly, charge increases regularly from element to element. So this charge will basically keep on increasing as we move from let's suppose this is the periodic table. So as you move from here to here, this charge will keep on increasing. Thirdly, nuclear charges will always turn out to be multiples of plus E. All right, and why is that so? So let's suppose we have an atom which is neutral, and we have minus E charges surrounding the positive nucleus. So obviously there has to be a plus E charge in the center, which will cancel out these, right? And another one was that protons, okay, each with a positive E charge, as I've told you before, provide charge to the nucleus, so that atomic number is the same as the proton number. So your atomic number Z is the same as the proton number. Thank you, and that's it.